Hi, this is A. Vimaladithan. My roll number is 24BEC0747. Today I'll be taking the topic of waves and equations which belongs to module 1. This is a very interesting topic which speaks about waves, oscillations, harmonic waves, standard waves, etc. Actually the type of waves and many things. So directly let's go into the topic. I'll be showing now a PDF or a PPT which is really helpful for us to understand the topic more easily. Okay, so let's start with the introduction to waves, module 1. As we know, generally this introduction to wave speaks about what is waves, what are the objectives of waves, different types of waves, classifications of waves, and many things else. To be simple, waves as a definition, like waves means wiggles in nature. That's it. In simple words, we can say waves as a wiggles in nature. So here are the classic objectives of waves, which we are going to see in our topic, which is what is wave and different kind of wave, as I said previously. The wave equation and its general solution. We'll be seeing the derivations, which was taught by us, sir, and I'll be displaying it and explaining it too. Derivation of wave equation and the further discussion belongs to. Okay. Uh, the definition, according to Optics Fifth Education, will be a classic wave is a self-sustaining disturbance of a medium which moves through a space, transporting energy and momentum. Okay. In introduction to waves, we'll be forming the wave formation and propagation. As we know, let's take an example. If you take a bowl of water, then you touch it with your hands or some objects, you'll be seeing a wiggles like a round, how to say it, eddy current. We will be referring to as an eddies in our physics as well. Like we will be forming a wave-like movement and wave-like nature in the water body, which is referred to as an wave. Let us first consider the example of water wave, which is the most familiar kind of wave that we can generate and observe easily. When we drop a stone in a lake or a water tub, we observe circular ripples that spread out from the point where the stone strikes the water surface, as shown in the figure. Looking at these ripples, you may wrongly get an impression for water moves with them, but no. But if you observe carefully, you'll notice that water actually does not move along with the ripples that are generated. As I previously said, they are the round-like ripples which are produced when we apply a force or we touch it with our hands, etc. Okay. Next, let's start with the wave formation and propagation, which is the main and the first topic of our introduction to waves. First, as we know, waves are two types, mechanical waves and non-mechanical. First, we will be seeing our mechanical wave. We can produce a mechanical wave using a thin and long elastic string with its one end fixed to a wall. Now, if you have to take a long string, which may be made of rubber, which will be really helpful. We will be taking a long string and using a thin and long elastic string, we'll be producing the mechanical waves. As we know, if we take a long elastic string, if you enlarge it and if you leave it suddenly, you'll be seeing vibrations. Vibrations are waves. Waves are known as vibrations. Both are same. As we know, in a wave, you can see in this you can see crest as well as trough. These both make a wave or the objectives of wave. Okay. Next, wave formation and propagation. From the above descriptions, we can say that a wave is generated due to two simultaneous at the same time distinct motion. The first one is the oscillatory motion of the particles of the medium, and the second is the linear motion of the disturbances. In wave motion, the propagation of a disturbance does not take place due to the physical movement of the particles in the medium. The disturbance actually propagates because of the transfer of energy from one particle to another progressively. Thus, we may conclude that the waves transport energy and not the matter. One like wave transports only energy. That's why we refer to as wave energy, thermal wave energy, or etc. Uh, the oscillation of a particle medium and the propagation of wave in the medium are intimately connected. As you can see examples in spring mass system as well as along with string. You can produce waves with more objects like strings, spring, etc. Now, classification of waves. As I previously said, waves are classified into two types: mechanical as well as non-mechanical. Based on the vibration of the particles of the medium, the waves are transferred into two types. They classified into two types, which are transfer waves as well as longitudinal waves. First, we'll be seeing what is transfer waves. Particles vibrate perpendicular to the direction of wave propagation, which is known as transfer waves. Coming to the next, longitudinal waves. Particles vibrate parallel to direction of wave propagation. Next, as we previously saw, based on vibration, we classified waves into two types. Now we will be classifying waves based on energy transfer, which is two types: standing waves as well as progressive waves. Without transfer of energy and momentum will be standing waves. Waves which transfer energy and momentum will be progressive waves. Simple. Okay. Next, let's see about transfer waves. The particle of the medium oscillate perpendicular to the direction in which the wave travels. As I previously said, in the transfer waves, particles oscillate perpendicular to the direction of the motion. Traveling waves on a taut string, the disturbances propagate along the length of the rope, but the particle oscillate up and down. Okay, next. Second, we'll be seeing the depth of the longitudinal wave. As we generally saw the definition at first in the flowchart, now we'll be seeing more depth concepts on longitudinal waves. In longitudinal waves, the oscillation of the particle is parallel to the direction in which the wave travels. In transfer waves, the particles travels in the perpendicular direction, but in longitudinal waves, it flows in parallel direction. So transverse means it's perpendicular direction, and longitudinal means it's in parallel direction. Okay. Next, I can say example for longitudinal waves will be a stretch string. If To be more depth in the example, we can say if one end of the string is suddenly given and out oscillation parallel to the length of the string, the coils of the string start exerting forces on each other, and the compression and the expansion points travel along the length of the string. The coils oscillate right and left parallel to the figure as shown. Okay. Next, we'll be seeing about longitudinal waves in sound waves. Like longitudinal waves, you can also as well as see longitudinal waves in sound waves, like in speakers or a sound producers or the sound produced will be traveling in the form of longitudinal waves. Okay, what are the difference between longitudinal and transverse waves? As I previously said, in longitudinal waves, the particles travel in parallel direction to the wave direction. But in transfer waves, it travels in perpendicular direction to the wave direction. Okay, next. Uh, Next, we'll be seeing about the traveling waves. Uh, these are the waves that propagate through time and space. The waves that propagate through time and space will be known as traveling waves. Examples: electromagnetic waves, sound waves, water waves, etc. Next, as we previously classified waves into two types: mechanical, non-mechanical. Then further we classified them into, based on the vibration, we classified them into transverse as well as standing. Now the transverse as well as longitudinal, sorry. Both are now done. Next we'll be moving on to standing waves and progressive waves. First we'll be seeing about standing waves. Standing waves are stationary waves which remain in a constant position with crest and troughs in fixed intervals. If the medium is limited in extent, for example, if you take a rope, they're reduced to a violent string fixed at both ends. The progressive wave traveling on the string would be reflected on both ends. The vibration of string would then be the combination of such waves moving to and fro along the string, and standing waves would be formed. Okay. And next, based on dimensionality. Based on dimensionality, the waves are classified into three types: one-dimensional waves, two-dimensional waves, and three-dimensional. Examples of one-dimensional waves are a wave on a string, two-dimensional waves are surface of water, then third, three-dimensional waves comes under sounds from a bell. Okay. Next, let's further see about two-dimensional or 2D waves. Examples of these 2D waves are water waves are visible to our naked eye. As I previously said, the ripples of water is also an examples of waves. Now it's an examples of 2D waves. A wave coming from a point source is circular, whereas wave originating from a linear source is straight. To be simple, the wave equation and its properties of velocity, wavelength, frequency hold true for two-dimensional waves as well. Okay, next we will be moving on to three-dimensional waves. Waves traveling in diaphragm walls or piles include different clusters of waves, usually named guided waves. Guided waves are mechanically stressed waves that propagate contained within the structural boundaries of pipes or plates with wavelengths that are comparable to the thickness dimensions of the pipe or plate. Guided waves are used in rapid testing, screening tools to detect, locate, and classify corrosion defects. Okay, next we'll be seeing about the properties of waves. As we know, generally the properties of waves are amplitude, period, wave speed, frequency, etc. Now we will be seeing in depth of the properties of waves. The first property of waves will be the wave speed. The speed of wave is the distance it covers in 1 second is the wave speed. It is different from the particle speed. Okay. Next, we will be seeing about wave frequency. What is wave frequency? The frequency with which the particles of the medium oscillate is known as wave frequency. To be simple, in transfer wave, frequency is the number of crests that pass through a point in 1 second. But in longitudinal waves, it's the number of compressions that pass through a point in 1 second. It is denoted by the symbol Gm. The SI unit of the frequency, wave frequency, will be hertz itself, which is equal to 1 cycle per second. Time period, which will be represented with a symbol capital T. The time period of the oscillation of the particles in the medium is the time period of the wave, and it's depicted in the figure as shown. It is denoted by the symbol capital T. The frequency of wave is the reciprocal of the time period. F is equal to 1 by T. So, frequency, or if they ask the relation between frequency as well as time period, you can just state this formula: F is equals to 1 by T. Amplitude. The amplitude of the wave is equal to the maximum positive displacement of the particles from their mean position. Thus, the amplitude of the wave is the same as the amplitude of the oscillating particles. Okay, next we will be seeing another property of wave, which is known as wavelength. This is the most important properties in the waves. The distance between any 2 points in the same state of motion defines the wavelength of the wave. Physically, this means that the wavelength is equal to the distance between two consecutive crests. The wave speed is given by, as you know, v is equal to lambda by t. Okay, where the lambda stands for the wavelength, v stands for the velocity of the wave, t stands for the time period. Since the frequency of the wave is reciprocal to its period, as we previously said, f is equal to 1 by t. The above equation can also be rewritten as f is equal to lambda by t. If you take v is equal to lambda by t, lambda into 1 by t, where 1 by t stands for f. So v is equal to lambda f. Okay. Velocities in wave motion. These are the three velocities in wave motion. There are three types of velocity, which are particle velocity, wave velocity, or group velocity. First, let us see about particle velocity. Particle velocity of a particle in a medium as it transmits a wave. The SI unit of particle velocity will be meter per second. Second, phase velocity. When a single wave of definite wavelength travels in a medium, then its velocity of propagation is called wave velocity. Okay, phase velocity will be equal to the wavelength by time period. As we know, F is equal to 1 by T. Then we are rewriting the equation as V is equal to F lambda on substituting the value of 1 by T. Then K will be 2 pi by lambda. As you know, by lambda stands for F. So omega will be 2 pi F. Okay, simple. Okay. Oh, in previous, K stands for the wave number. Okay. Yeah. Now let us see about the relation between particle velocity and wave velocity. Let's first consider the equation of plane progressive wave, which is equals to y is equal to a sine omega t minus kx. In particle velocity vp, we will be representing particle velocity as vp. Vp is equal to dy by dt is equal to, as we differentiate the equation 1, we will be getting a omega cos omega t minus kx. Now we will be doing the slope of displacement, where dy by dx is equal to minus ak cos omega t minus kx. On dividing the equation 2, which is vp is equal to dy by dt is equal to a omega cos omega t minus kx. On the third equation, we get dy by dt minus dy by dx is equal to omega by k, where omega by k stands for wave velocity. So particle velocity will be equal to the negative of wave velocity into strain. Particle velocity changes with the time, but the wave velocity will be constant in a medium. Okay. Next, we will be seeing out the group velocity. If a number of different wavelengths are moving with a different velocity in a medium, then the observed velocity will be a group velocity. Simple. Okay. Next, we will be moving on to the superposition principle. Superposition of waves and group velocity. Considering the superposition of two waves of nearly equal frequency, omega 1, omega 2, with same amplitude A. In the individual displacement for each wave are y1 is equal to a cos omega t minus k1x and y2 is equal to a cos omega t minus k2x. The superposition of their amplitudes and phase gives y is equal to y1 plus y2, where we will be adding both the equations. We will be getting 2a cos omega minus omega t omega 2t by 2 minus k1 minus k2x by 2. Similar, we will be following the further steps. The resultant displacement of the superposed waves has maximum amplitude of 2a and frequency omega 1 plus omega 2 by 2. Okay, it can be seen through the resultant displacement as modulated in space and time. Okay, this will be the figure for superposition of waves. We doesn't want to go much depth in this topic, so let's move on to the next topic, which is about harmonic waves. Okay, the harmonic waves are oscillatory in nature. As we know, let us first see the solution of harmonic waves. In the solution of harmonic waves, y x comma t will be a sine kx minus omega t. The general definition for harmonic wave will be a wave with frequency that is integer multiple of a fundamental frequency. The fundamental frequency is also known as the harmonic wave. General definition will be an harmonic is a wave whose frequency is whole number multiple of the frequency of a reference signal. Okay. In you as next we will be seeing about the Euler's formula, which is ei theta is equal to cos theta plus I sin theta, in which we will be seeing further terms or the further formulas for the properties of waves. As we saw, the properties of waves will be time period, frequency, wave number, etc. Now we will be seeing their respective formulas. Okay. First, for velocity, v is equal to omega by k. For time period, t is equal to omega by v. If for f is equal to v, which is equal to 1 by t. For velocity, v is equal to lambda v. For omega, which is angular frequency, we will be writing 2 pi by t, which is equal to 2 pi by v. For wave number, k is equal to 2 pi by lambda. Okay. The final topic will be the wave nature. We will be further discussing about the wave nature, and most importantly, we will be seeing about the wave equation. Okay. Now I will show you a PPT which belongs to the. Okay. No. Now I'll be showing about the full derivation of a wave equation. Okay. This was taught by our sir Samir Ranjan Meher and sorry, Dr. Samir Ranjan Meher. He taught us this equation, which is very easy to understand. If you listen the topic more more concentrate with more concentration, you can see the wave equation. First, I will be displaying the images of the topics respectively. Okay. 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 In this is the diagram of the first wave equation where xt stands for displacement, and we will be writing the formula for f, which is a frequency, which is equal to m dx by dt square. Then further we will be writing as f net m d square x by dt square. Next step. Okay, we will be moving to the algorithm of the wave equation. As you see, the algorithm of the wave equation, uh, in this algorithm means what are the things we gonna see in the wave equation, or what are the things we gonna use in wave equation to form the final wave equation. Okay, the algorithm of the wave equation will be obtain the displacement of a small segment of the vibrating string. Second, identify the net force applied on the string. Third will be Newton's second law of motion. Okay. At first, we found out the force acting a net force acting on the string, which is equal to F net is equal to m d square x by dt square. As previously mentioned, by mistake I mentioned it as frequency. Sorry, it will be the force acting on the string. Okay. Let us see the first diagram, which in which there is a diagram or graph in which y-axis stands for displacement and x-axis stands for propagation direction. As you see, it's a type of a sinusoidal wave. If we magnify the graph of the portion, we will be seeing the second magnified part of the graph 1, in which mu stands for the linear mass density of the string. We must definitely consider the linear mass density, whose SI units or the units will be kilogram per meter. Then m will be the mass of the small segment, which we gonna consider for the wave equation. Okay. Next will be next will be Ft, which is how the force of tension along x-axis. F2 will be the restoring force, which is mentioned in the graph. F1 will be the displacement force. These are the terms which are involved in the graph 2, which is the magnified uh, photo or a magnified graph of the graph 1. Okay. Uh, the main important point in wave equation will be ignoring the gravitational force. Gravitational force must be ignored. It should not be considered. Okay. In which theta 1 and theta 2 are very small. So sine theta, this we can write it as tan theta, since theta 1 and theta 2 are small. So tan theta 1 will be minus f1 by ft. Tan theta 2 will be f2 by ft. Now let us consider the slope, which is dou y by dou x, in which tan theta 1 is equal to dou y by dou x, x1 is equal to minus f1 by ft. Tan theta 2 will be dy by dx, x2 is equal to f2 by ft. Okay, next step. Let us calculate the net force. Now we have calculated the values of F1 as well as F2. Net force means F1 plus F2. So we'll be adding the both equations, where F1 stands for minus Ft dou y by dou x x1. F2 will be standing for Ft dou y by dou x x2. Okay, F net will be F1 plus F2, where when we add this, F2 will be dou y by dou x x2 comma t minus dou y by dou x x comma t, which is equal to Ft dou y by dou x x plus del x comma t minus dou y by dou x x comma t. From Newton's second law of motion, we can consider F net will be mu into del x dou square y by dou t square. Further calculations will give you dou y by dou x y x plus del x t minus dou by dou x y x comma t by del x is equal to mu ft dou square y by dou x square. Okay, next step. Next, we'll be moving on to the final page of the wave equation, where del x must be considered as 0. Okay, del x must be considered as 0. Okay, fx will be dou of fx by dou x is equal to limit h0 f of x plus h minus f of x by h. Now we will be applying the limit del x tending to 0, like dou y by dou x x plus del x comma t minus dou y by dou x comma t by del x is equal to dou square y by dou x square. Dou square y by dou x square will be mu by ft dou square y by dou t square, where mu by ft stands for velocity into velocity, which is equal to velocity square, which is equal to 1 by v square, where mu by ft will be v square. Then we will be substituting the value of mu by ft, which is 1 by v square, in the equation. So we'll be getting 1 by v square dou square y by dou t square. V square is equal to ft by mu. Okay, and v then finally, if the square moves to that side, we'll be getting the square, which is root of ft by mu. Okay. Next, these are the this is about all about wave equation. which was taught to us. Next, finally, we'll be seeing the last topic. Give me a second. Okay. Oh, this will be the diagram I forgot to show of harmonic wave. It's similar to a sinusoidal wave. Doesn't want to explain as such. Okay. Mm, okay. Next, again, we'll be seeing about the wave equation derivation with more simplified manner. Now I'll show you. Wait. Okay. Now let us see about the wave equation derivation again with more simplified manner. Now, consider a string of mass m making oscillation along y-axis, which is perpendicular to the direction of propagation x-axis as shown. As shown in the graph, we'll be considering the string of mass m and which is perpendicular to the direction of propagation. Assumptions. In previous, we made algorithms, which is uh, the algorithms will be obtaining the displacement of small segment of vibrating string, identify the net force applied on the string, and considering the Newton's law of motion. In this assumptions, we'll be seeing assume mass per unit length is constant. The linear mass density will be rho by m by del x, which is equal m is mass will be equal to rho del x, in which in this string is perfectly elastic. Then gravitational force is negligible. As I previously said, gravitational force should be ignored for the wave equation derivation. The string makes small oscillation. As we know, the strings makes small oscillations. Theta 1 and theta 2 will be small. So instead of considering sine theta, we'll be considering tan theta. It is because the string produces small oscillations. Now, first, let's see the force acting on the element del x at an angle theta at one end P and P at an angle theta plus del theta at end Q. The perpendicular force on the element will be del x is equal to T sine theta plus del theta minus T sine theta, where ma on considering the Newton's second law, which is mass into acceleration, we will be writing m d square y by dt square. Okay, next, uh, we will be writing the equation. As you know, m stands for rho into del x and a stands for dou square y by dou t square. On substituting these values, we will be getting t sine theta plus del theta minus t sine theta is equal to rho del x dou square y by dou t square. As the string produces small oscillation, the small angle theta, instead of using sine theta, we'll be using tan theta. We know that tan theta is equal to dou y by dou x, tan theta plus del theta by dou y by dou x, x plus del x. Equation 1 becomes on replacing sine theta with tan theta. So t times of tan theta plus del theta minus t tan theta is equal to rho del x dou square y by dou t square. Then t dou y by dou x of x del x minus dou y by dou 2 is equal to rho del x dou square y by dou t square. Then on applying limits where del x tends to 0, and previously I said y x plus del x minus yx by del x is equal to dou y by dou x. On replacing y with dou y by dou x, the limit extending to 0 will be dou y by dou x minus dou y by dou x by del x is equal to del x dou square y by dou x square. On substituting these values in the equation 2, we'll be getting dou square by dou x square equal to rho by t dou square y by dou t square. As you know, rho by t can be written as 1 by c square, where c is equal to rho by t by r. Dou square y by dou x square is equal to 1 by c square. Dou square y by dou t square is the wave equation, and c is the velocity of the wave. So this is my derivation based upon the wave equation It may be different from sir, but it looks more or less similar. Okay, next, I'll be showing the next standing waves on a string of fixed length. For Z2 is equal to infinity string tied with a rigid wall with the fixed ends at x is equal to 0. Hence, no transmission is allowed at x is equal to 0. This implies reflection coefficient is equal to minus 1. To be this instant wave is fully reflected, the phase change of pi. That means a string fixed at the both ends experience infinite impedance at the ends. Instead, traveling wave is fully reflected from both the ends. Okay. Now consider a monochromatic wave, which is single frequency wave traveling with a frequency omega and amplitude A in the positive direction, x and amplitude B traveling in the opposite direction, which is mentioned as negative x. Then the displacement of the string at any point x is given by y is equal to a e I omega t minus ax plus b e I omega t plus x. At boundary condition y equal to 0 and at x is equal to 0. Second boundary conditions will be y is equal to 0 and x is equal to L. The conditions y equal to 0 and x is equal to 0 gives 0 is equal to a plus b e I omega t for all. Therefore, A will be equal to minus B. On concluding that a wave in either direction meeting the infinite impedance at either end is completely reflected with a pi phase change in amplitude. The expression of for y becomes y is equal to ai omega t e minus ikx minus e ikx is equal to minus 2i a e power I omega t sin kx. The boundary condition that y is equal to 0 x is equal to L, which will be the second boundary condition. On seeing this, the allowed frequency are given by omega n is equal to n pi by c by L, Vn is equal to nc by 2L, which is equal to c by lambda n. Vn is equal to nc by 2L, as we previously say, c by lambda n, which will be c will be the velocity of the wave. The frequency are the normal frequencies or mode of vibrating or aging frequencies. Such allowed frequencies define the length of the string as an exact number of wavelengths. Okay, the string displacement of the first four harmonics can be seen as n is equal to 1, n is equal to 2, n is equal to 3, and n is equal to 4. The frequency corresponds to n is equal to 1 is called fundamental or first harmonic. Frequency corresponding to n is equal to 2 is called the second harmonic, and so on. Nodes or nodal points are the point of zero displacement for all t occurs n minus 1 in the number of each harmonics. Okay. Finally, we come to the end of our module one, which is wave equations. And I mean waves, the properties of waves, types of waves, classification of waves. We saw many things like wave equations, etc. So this will be our end of the topic and end of the video. Meet you in the next video. Until then, this is Vimal signing off. Thank you.